Welcome to Online Algebra 2. Today, we are going to cover section 6-7, inverse relations and functions. All right, so our objective here is to find the inverse of a relation, okay, or a function, right? And we'll talk about the difference between relations and functions again in case you forgot it. All right, so and our essential understanding is that the inverse of a function may or may not be a function itself, right? So we can find just like we can have a relation that is just data. Uh, this data could have an inverse, and that inverse may or may not be a function. Okay, so to remember what a relation was from I think that was section 2.1. So a relation is just something that has some sort of input and some sort of output. So if a relation pairs an element of the domain A with an element of the range B. If this is the relation, okay, the inverse relation switches them. So it takes B as the input and A as the output. So remember, this is input output. So A is the input of the function and it spits out B. In this case, when you put B into the inverse, it would spit out A. So if AB is an ordered pair of any relation, then BA is an ordered pair of the inverse. And if both of these are functions, then we call them inverse functions. And remember, the way you tell a function versus a relation, relation is anything. A function is a specific type of relation where every element of the domain is paired to one element of the range. Okay? So let's look at this. This diagram shows a relation, R, this one, and its inverse. So everything in the domain goes to one thing in the range. The relation is a function, but now when we switch these two, we switch the inputs and the outputs. We take all the x's and we make them y's. All the y's become my x's. That's how we get inverses, right? We're switching x and y. But notice that now the inverse of this relation is not a function anymore because one is going two places. It's fine, it's still data, okay, but it's just not a function. Let's try it. So what is the inverse of relation S? Well, here's my relation S. The way I make an inverse, so let's call this inverse of S, okay? So the way I switch it, or the way I make my relation is I just take every x and make them y's. So this would be 0, 2, 3, 4. And I take every y and make them x's. 0, 2, 3. So instead of 0, -1, I have -1, 0. Instead of 2, 0, I have 0, 2. Okay, and you get the idea. Let's take a look at these graphs. Okay, so the 4 points of my original function were 0, -1. So that's right there. 2, 0, right there. 3, 2, 3, 1, 2, and 4, 1, 2, 3, 4, 1, 2, 3, right there. Okay, so that is my relation. Let's switch over to red here, and now let's graph the inverse of the relation. So instead of 0, -1, we have -1, 0. Instead of 2, 0, I would go 0, 2. Instead of 3, 2, I would graph 2, 3. And instead of 4, 3, I now have 3 and 4. And you can sort of see that this is a line in the middle of them. And they've just sort of been reflected over this line, which if you look at this line really carefully, it has the equation of y is equal to x. Okay, that's really important. We'll come back to that. Okay, let's try this problem again. Okay, with our got it problem. So if that is the relation, the inverse would be the y's turned to x's, so that's -5, -4, -3, -3, and the x's become my new y's. Okay, so let's graph both of these. 0, -5 is down there. 1, -4, 2, -3, and 3, -3 as well. So there's my relation. Here is the inverse. -5, 0, -4, 1, -3, 2, and -3, 3. And you can see now that since -3 goes to 2 places, right, and we fail the vertical line test, the inverse of t is not a function anymore. But also, look at this. They are still reflections of all these points about the line y is equal to x. Okay, that's good. Okay, so when we look at this problem, problem 1, the graphs of a relation and their inverse are reflections of each other across the line was y is equal to x. Okay, that's what I just said. So if you describe a relation or function in an equation, right? This is data. It's pretty easy to just switch the data around, right? Switch the two columns, right? It's pretty easy to have a picture and just reflect all the points, just reverse the points, right? Reflect them over the line y is equal to x. But if we have an equation, we're going to need a way to get my equation of my inverse, okay? And the way you do that is we're going to use something called the switch and solve strategy. So we're going to switch x and y to get an equation for the inverse. And here's a breakdown of that strategy, okay? So if it's in function notation, we're going to change f of x to y. They're interchangeable, right? They mean the same thing. But in terms of finding the inverse, we're just going to want y, because then we're going to leave everything in the problem exactly in the same place. The only difference is the letter x I changed to the letter y, and the letter y I changed to x. Then solve it. Get y by itself. Okay? If the equation does not define y as a function of x, the function f does not have an inverse function. All right. So now you can stop. You can just say this is the equation, but it's not a function. If it is a function, right? Now we have a special notation. This is my notation for a function, right? F of x. This is my notation for an inverse function. F little -1 exponent, but it doesn't mean an exponent, right? It's just notation. It's just saying the inverse of x. And we'll talk about what this means later. Okay? So, my switch and solve strategy. First step said, if you have f of x, change it to y. I don't. I already have a y. So, my equation is simply x squared minus 1. Now, with this strategy, what we do is we take the y, I change it to an x. I take the x, I change it to a y. I don't change the squared, I don't change the -1. All I literally do is take those two and switch them. Now, in order to get the equation for my inverse, I need to get y by itself. So that's x plus 1 is equal to y squared. Take the square root of both sides, and then I'm going to use the reflexive property here to write it the other way. Remembering that when I take the square roots of both sides of an equation, you have to put plus or minus. Okay, and now in this case, this would not be a function because an input into x would give me two answers, right? If I plug a 1 into, or if let's plug an easy number in there, 0. So I would get +1 and -1. Okay, so it doesn't work. It's not a function, right? You can still find the equation of the inverse. Yeah, there it is. Okay, it just doesn't happen to be a function. Let's try this line. Okay, what is the inverse of y is equal to 2x plus 8? So I go y is equal to 2x plus 8. I switch and solve. So I take the x, I put it there. I take the y, I put it there. Okay, I just switch x and y. Now just get y by itself. So subtract 8. X minus 8 is equal to 2y. Divide out the 2. So y is equal to, and then I'm just going to reverse these because I like to have y over here on the left. So that's 1/2 x minus 4. Right? 1/2 x. Okay. So that is the switch and solve strategy. Okay. And now this happens to be a function, right? Because one input gives me one output. Every x gives me one y. So then I could start to use my function notation, which we'll look at in a second. Okay, so this was the first problem here, right here, right? I started with y is equal to x squared minus 1, and I got this plus or minus thing. So let's see actually what it looks like. So what is the graph of this? And then let's look at the graph of the inverse. All right, so first, you should recognize this as a parabola. So when I graph this, it's a parabola with a vertex at 0, -1, is moved down 1. And then I can just plug in the other numbers here to get it, right? If I plug in 1, I get 0. 1, 2, 3, 4. And 3, 1, 2, 3, 4. Right, because there's no up 9, right 3 up 9, because there's no stretch or compression on this. And now I know that it is like that because all parabolas are symmetric. So here is my graph of x squared minus 1. Okay, now let's take a look at this graph. Okay, let's make a little table for it myself. Okay, and I'm only going to use numbers that actually make sense. And even better, I could just use these points right here, right? Because I know that this function has a coordinate of 0, -1. That means that the inverse has a coordinate of -1, 0. And let's actually try that. If I plug in -1, right, I get -1. So that's plus or minus 0, right? Plus or minus 0 doesn't mean anything. It's just 0. So we get this. All right. Well, this point right here was 0, 1, and 0, -1, which means I should get those two as coordinates. And it actually works because if I plug in 0, I get 0 plus 1, square root of 1 is 1 plus or minus, so I get plus or minus 1. Okay, so that's 0, 1 right there, and 0, -1. And I can do the same thing here. So this is 2, 3. So we get 3, 2, and -1 down, or -2 down there. Okay, and then for these, this is 3, 8, and so I would get 8, 5, 6, 7, 8, 3, and like this. And you can see that the two graphs are reflections of each other, with this line right here, the line y is equal to x, being the middle. Okay. We can do that again for the got it problem. So the equation of the inverse was y is equal to 1/2 x minus 4. Okay, so if I graph both of these, 2x plus 8. So there's my 8 right there, intercept, up to right 1. So here's my line, something like that. And then if I graph the 1/2 x minus 4, so I start there, up 1, right 2. And you can kind of see that these again are reflections of each other across the line y is equal to x. Okay, so that's really what the point of these problems were, is that when you have the inverse, right, we have a way now to get the equation of the inverse using my switch and solve strategy. And when I'm thinking about the graphs of a line and its inverse, or of a parabola and its inverse, they're always reflections of each other across the line y is equal to x. You just take every coordinate and you can reverse them. Okay, so now clearly the red one, not a function, fails the vertical line test. Both of these here are functions. They're both two lines. Okay, so when we have a function whose inverse is also a function, we're going to use this special notation. So this f of x represents my original function. F inverse of x, that's the way you read it, right? We don't read f to the -1 power. It's called f inverse of x, is the notation for inverses. Okay, only use this notation if the inverse happens to be a function. If it's not a function, like the plus minus with the radical, we just leave it as y is equal to that. Okay? Everything doesn't have to be a function. Okay. Now, of course, normally, if we were using a negative exponent, right, we would move that to a bottom of the fraction. That is not a negative exponent. It is just a notation, right? It's just telling you that this, whatever it is related to some other function, and they are related because they're inverses of each other, and one is a reflection of the other across the line y is equal to x, right? So let's make an inverse function, and let's think a little bit about domain and range. Okay, let's start with this function, square root of x minus 2. Well, the domain and range of this function is a little limited, right? The domain of f of x is anything that I am allowed to input into this function to keep no negatives in the radical, right? Because I cannot have a negative radical or else I would get an imaginary number. So for instance, if I plug 0 into this function, that's no good because now I have the square root of -2. But if I plug 2 into this function, that I can do, and I can take this all the way up to infinity. So the domain of this function starts at 2 and keeps going up to infinity because I can plug any other number I want here and I'm going to get a positive radical. They're not all going to work out, but that's okay. The range is from 0 to infinity because I can't plug anything less than 2. And as I keep plugging bigger and bigger and bigger, if I plug 2 in here, I get 0. But as I keep plugging bigger and bigger and bigger and bigger numbers in, this just keeps getting bigger, right? So it's never going to go back to being a negative. All right, so the reason why we did that is because when I find my inverse function, x's and y's switch places. So since domain represents x's and range represents y's, these two are also going to switch places, and watch what happens. So my function was f of x is equal to the square root of x plus 2. No, minus 2, sorry. Okay. So what am I going to do? I change this to y, and then I switch and solve. Okay, so let me rewrite that over here. X is equal to the square root of y minus 2. I'm just going to square both sides. So I have x squared is equal to y minus 2. And just add 2 to both sides. So that gives me y is equal to x squared plus 2. Okay. But, okay, this is a parabola. Okay. It would normally be a picture that kind of looked like that. Okay. But this function is a square root function. Okay. Which means that some of the answers I wasn't allowed to plug into this. So that means that I'm not going to be able to get all these points back here because my original function didn't have any negative inputs. So that means that the domain and range of my inverse function is going to be limited. Okay? And again, since x's and y's switch places, the domain goes from 0 to infinity. And the range, right, if I plug 0 in here, the lowest thing I can get is 2. Okay? And now my inverse function, f inverse of x, is going to be equal to x squared plus 2. Right? I just take y and I put it back to f inverse of x. So x squared plus 2, as long as x is greater than or equal to 0. Okay? The domain. Okay? So this function is defined all for any positive or negative numbers, but I have to limit it because my starting function was limited. So is this now a function? Is this a function? Yes. It is a limited function. It's half of the full picture of a parabola, but it is a function. Okay? There's only one value of x that I can get in output. Let's try one that's a little more straightforward. Let's try a line. All right, so we start with my function. So in this case, it's g of x is equal to 6 minus 4x. I replace that with y. I switch and solve. So we have x minus 6 is equal to negative 4y, and divide everything by negative 4 to give me y is equal to negative 1/4 x plus, let's just reduce it, 3/2. Okay? And is that an inverse function? Yes. So f inverse of x, quarter x plus 3/2. So what did I just do? Domain, this is a line. The domain is all real numbers, the range is all real numbers, and so the domain and the range of f inverse of x is also all real numbers. Right? The only things that limit domains are square root functions and variables in the denominator, right? You got a square root function, it can't have anything inside that makes it less than 0. If I have a variable in the denominator, I just can't have the denominator be equal to 0. Okay? So that was switching and solving and then writing it as an inverse function. Okay? Now, the one difference with this is that functions that model real world behaviors are often expressed as formulas, like a is equal to pi r squared, like area of a circle is pi r squared. The inverse, right, if I switched and solved it, if I switched a and r and solved it, I would get this. But that is a false relationship between area and the radius. So when we have a real world formula, we're just going to be solving for the variable. Okay, so this technique doesn't work if you have um, basically word problems, okay, like this. So the function d is equal to 4.9 t squared represents the distance d in meters that an object falls in t seconds due to Earth's gravity. Find the inverse of this function. How long in seconds does it take for the cliff diver shown below to hit the water? Well, okay, so I want now time by itself. Okay. All I have to do here is just isolate time, right? We're not switching, right? So we just have d over 4.9 is equal to t squared. And then I just take the square root of both sides, and I get that t is equal to, now, I could put plus or minus. I don't really have to because time is not going to be negative. So I can just leave it positive. The square root of d over 4.9, plug in my distance to solve this problem, use a calculator, and we get it's about 2.2 seconds. Makes sense. Jump off a cliff, 2.2 seconds to hit the water. Sort of makes sense. Okay. So when we have a word problem, when we have a relationship between area or distance, time, velocity, whatever, right? And you're trying to find inverses of a formula, right? That's the key word here, formula. If you're trying to find the inverse of a formula, then we just rearrange the equation. We just rearrange the formula. As opposed to the equations that we were doing in the beginning, you have to use a switch and solve strategy. Okay, so you know that for any function f, each x value in the domain corresponds to exactly one y value in the range. For special functions called one-to-one functions, it works both ways. So it's true that each y value in the range corresponds to exactly one value in the domain. So basically that means that your input gives you an output, and that output only gives you one input, okay? So that means x is never repeat and y is never repeat. It also means that one-to-one functions, if we have a function, the inverse is also a function. So that's basically what one-to-one functions are, is it's just a function that has an inverse that's also a function. It means x is never repeat and y is never repeat, okay? So if that is true, if f and f inverse are inverse functions, then if you put a composition of the inverse of the original function of x, these two are going to undo each other and you're going to go back to where you started. And the opposite is also true. F of f inverse of x is equal to x. And right, so if you put the inverse into the original function, everything will undo each other and you will go back to where you started. This is the technique to prove that two functions are inverses of each other. Okay, so if you had a function and you want to say, hey, which one are these two things inverses of each other? You plug one into the other and see if you just get the variable by itself, and then you do it the other way. So with a function like this, let's find the inverse first. Okay, so to find the inverse here, the inverse function of x, so we would say y is equal to 1 over x minus 1. I would switch x and y, and then get y by itself. Now, I don't really want to add everything to both sides, so let's just multiply both sides by y minus 1. That cancels that. So we have y minus 1 times x is equal to 1. Then just divide out the x. So y minus 1 is equal to 1 over x. And now y is by itself. So y is now equal to 1 plus x, 1 over x plus 1. Okay? Seems like a function. Okay, so the inverse function is squeeze it in here, 1 over x plus 1. All right, great. Now, let's see if these two things are inverse, are 1 to 1. Okay, so that means that for any value, okay, if I plug the inverse into the original function, I should get 1 when I'm done with this. So let's try it. So we want to do f of f inverse of 1. Okay, so I'm going to do this one first. So I'm going to do f inverse of 1. F inverse was 1 over x plus 1. So that's 1 over 1 plus 1, which is 2. Okay, good. So now I take that answer, 2, and I plug it back into the original function. That's how compositions work, right? So we plug 1 into the inverse function, and now into the original function, which was 1 over x minus 1, we plug in 2. So that's 1 over 2 minus 1, which is 1. Hey, look at that. I got back to the beginning. So this checks out. But if we look at the opposite, if we try to do f of 1, now, oops, 1 over x minus 1 was my original function. If I try to plug in 1 there, that is undefined. Okay? So you just have to be careful to make sure that you are including, oops, we're including x that are in the domains of f and f inverse, okay? So in this case, there should have been a restriction here that says we couldn't use 1 if we're composing these two functions together, okay? And that was 6, 7. Most of these are pretty straightforward. Yeah, we'll leave it here. That's 6, 7, inverse relations and functions.